Okay, so good day everyone. So now let's proceed to our next topic guys, which is the analysis of singly reinforced beams. Okay, so here are the procedures in the analysis for rectangular singly reinforced beam section, specifically for Nacp 2001. Okay, so we all know that if we try to analyze a particular beam section, then we are tasked to determine the ultimate moment capacity of the section. So that is given the properties of beam, which is the AS, the B, the D, Fy, and the F prime C. Okay, so for the first procedure, so we are tasked to solve for the steel ratio, which is equal to rho is equal to AS over BD. Okay, then after that, step 2. So we'll try to check if the steel yields by comparing the value of rho and rho balance. Okay, so we're in if rho is greater than 0.75 of rho balance, therefore the ductility requirement provided as for section 410.4.3 was not satisfied, while if your rho is less than or equal 0.75 of rho balance, so ductility requirement provided in section 410.4.3 was satisfied. So just review this particular section. I think we have discussed it already on the concepts of chapter 3. So if rho is less than rho balance, then your tension steel yields. So this is desirable since your design is under reinforced design, or in 2010 that is tension controlled. So therefore your Fs is equal to Fy, wherein if your rho is greater than rho balance, then tension still does not yield. So meaning this is over reinforced, or your design is compression controlled. Okay, so therefore your Fs is less than Fy, so it didn't reach your steel didn't reach the yield strength required. Okay, so you will be using Fs in your analysis. So for step 3, calculate the ultimate moment capacity based on the condition. So if your rho is less than rho balance, then just try to calculate the depth of compression block. Then automatically you could solve the ultimate moment capacity. Okay, so this is the formula. So you could automatically use Fy now, since your steel yields. Okay, then your ultimate moment capacity would be rho AS Fy times D minus A over 2, or you could also use phi 0.85 F prime CAB times D minus A over 2. Okay, how about if your rho is greater than rho balance? Then you try to express the actual stress of the tension steel to Fs. Okay, express it to Fs, wherein we will expect that it is less than Fy since steel does not yield, and substitute the expression to the equation 0.85 F prime CAB is equal to AS times Fs. So therefore we couldn't automatically use or calculate the depth of compression block since we'll be using Fs instead, since your design is over reinforced. Okay, so we will try to solve Fs now by solving C first, wherein C is equal to 0. C over 0.003 is equal to D minus C over Fs over E of the steel, which is 200,000 MPa. So this is simply the ratio and proportion, okay, in the illustration. So the illustration here. Okay, so this is C, then this is D minus C, Then in here, this is Fs over Es. That is your strain S na for your steel. Okay, so simplifying, so you have Fs now, which is equal to 600 times D minus C over C. Then your formula now would be equal to, so this is C is equal to T, but this is 0.85. Instead of F prime C, instead of using A, then you should substitute it with beta 1 times C, because take note that A is equal to beta 1 times C. Then this is equal to AS. So instead of using Fy, then you will be using Fs. Now wherein Fs is 600 times D minus C over C. Okay, so you will be getting a value of C here. Okay, so you will be we're getting a value of C here. Distance C, distance from the compression steel fiber or compression fiber, then to the neutral axis. Okay, so but always be careful in using shift solve for this equation, because there are tendencies that the values for C would be negative and positive, and sometimes the calculator gives you a negative value of C. So always consider the positive one. Okay, now after getting the value of C, then you'll be getting A, now the depth of compression steel block. Then after getting the compression steel block, then we could calculate now the ultimate moment capacity of the section. Okay, so that is for this condition. Okay, that is for 2001. So next procedure is for the analysis of rectangular singly reinforced beam sections for Nacp 2010. Okay, so for Nacp 2010, so your first step is to calculate the values of A and C. Okay, so in calculating the values of A and C here, you assume that that your section is tension controlled. Okay, why is it that you assume that it is tension controlled? Since the formula that you will be using for A utilizes the term Fy, or the yield strength. You will utilize the yield strength. So that's why it is considered the assumption of tension control. Okay, then you have C as well. Then now you try to calculate the value of the strain at the tension steel. So that is E sub T, or epsilon sub T, wherein epsilon sub T is equal to dt minus C over C, then times 0.003. So again, this is from the strain diagram, specifically in think in tension control, in tension control diagram. Okay, so so this is a formula for strain at the tension steel. So now we have we need to check the ductility requirement. Okay, so using these two conditions here, wherein if your strain at the tension steel E sub T is less than 0.004, then the ductility requirement provided in section 410.4.5 was not satisfied. Okay, so therefore the beam section may not be used. So there would be changes that must be made on some properties of your beam, maybe the dimension or the diameter of the bar, or the property of the bar, or the property of your concrete. Okay, But if your epsilon sub t is greater than or equal to 0.004, then the ductility requirement was satisfied, so therefore the beam may be used. Okay, so how about for the section or beam conditions? So we have these three conditions here that we have discussed already, which is the tension controlled, the we have transition region, and we have compression control. Okay, so if your E sub t is greater than or equal to 0.005, then your design is tension controlled, so we don't have any problem here. No, if your design is tension controlled. But if your E sub t is greater than E sub y, and that is less than 0.005, then you will be in transition region. Okay, so we're in your epsilon sub y. Okay, so your epsilon sub y would be the Fy na Fy over Es na of the steel, modulus the elasticity of steel. Then if your E sub t is less than or equal to E sub y, then you are in compression control. Okay, so if compression control, then you need to recalculate the values of your A and C and solve for Fs. Okay, so therefore your assumption, okay, your calculated A and C here now on the first step is not valid now, since your steel does not yield. Okay, so you will be using Fs instead. Okay, then for step 3, so you need to calculate the reduction factor P and the ultimate moment capacity of the section. Okay, so there are varying values for reduction factor. Okay, so for different conditions of the sections. Okay, so same formula guys for calculating the ultimate moment capacity. Okay, so let me discuss this one here. Now for this is figure 3.5 in the McCormack book. So this is the variation of the reduction factor P with the net tensile strain E sub t and C over dt for this. Take note guys, this is for the reinforcement. Okay, so take note, this is for this one for grade 60 reinforcement and for pre-stressing steel. Okay, so as you notice that in the first on the row, when row is 0.65, then that is from 0.65 to E sub t, which is 0.002, so that is compression controlled. Okay, so you will notice that phi there is 0.65 only. Then for E sub t, okay, so let me redraw it guys. No, let me redraw it, okay, to at least clarify the illustration. Okay, this one here is E sub t, then this is phi value. No, so if we from this starting point, which is the origin, then until your E sub t is 0.02, then the value of your phi here is 0.65. Okay, okay, that is 0.65. Okay, so this is So the red one, so this one here is the compression control. Okay, that is compression controlled. Okay, so based on this diagram here, then we have this inclined line here, no? So we have, okay, so from this one, then going to that direction. Okay, so your E sub t here is 0.005. Okay, so any value, okay, any value of E sub t that is greater than 0.005, this would be considered as tension controlled. Okay, that is tension controlled. And for tension controlled, okay, so for tension controlled, your phi value here is 0.9. Okay, so we don't have any problem with tension controlled and compression controlled. Okay, so the only thing that we need to consider is the transition region. Now that is in between compression and tension controlled. Okay, so this one here, so this one here is, okay, so this one here is the transition okay, so this is a transition region. Okay, then we have a formula, okay, for phi, which is 0.65 plus epsilon t minus 0.002 times 250 over 3. Okay, so for that transition region there. Okay, so this is the formula for phi here. Phi value, say any value, no, yeah, that one. So phi here is equal to 0.65 plus strain t minus 0.002 then times 250 over 3. Okay, so that is the formula there. Now for the transition, for the reduction factor, transition region. But take note, guys, that this is Fy is equal to this is Fy, which is equal to 414 MPa, or this, or your steel is grade 60. Okay, so grade 60 and a press dressing steel. Okay, so the question here now is, how about if your Fy or the steel grade is not a grade 60 steel? Okay, so that is the question now. So we need to redraw. Okay, so we need to redraw that one. Okay, so let me redraw that one here. So we have strain T, then we have phi. Okay, then again this is phi is 0.65 here. Okay, for the, okay, so this is for the compression controlled, okay, region. Then Okay, and then this one here. Okay, so beyond this one is the tension control. Then this one is the transition region. Okay, so this one here is the transition region. So we have phi here. Okay, so we have phi here, which is 0.9. Okay, so now since the condition for TR, okay, so take note that the condition for TR is that your E sub T should be greater than E sub Y but less than 0.005. Okay, so this one here, your this is E sub T, which is equal to 0.005. Okay, then say if you wanted to get a P here at a certain a point, no, certain point of the transition region. Okay, so you wanted to get a phi value there, no, and this is the value of your E sub T, no, E sub T. So let me change this one here simply as 0.05, okay, to lessen the confusion. Then the value here, since it exceeds the E sub Y. Okay, so notice that we will have a triangle here. No, so we have a triangle here, this one here. Okay, so we have a right triangle here. Okay, so we have also a right triangle here. So you will be using the two triangles for similar triangles, for similar triangles. So similar triangles. So we have this small triangle, guys. Now we have this small triangle. So this is this side here. This side here would be equal to rho minus 0.65. Okay, so this one here, this is phi minus 0.65. okay, from this distance here, take note, this is phi, then this one here is 0.65, right? Now, so if we will have a Cartesian plane, then this one here is equal to strain T minus strain Y. Okay, so again, that is coming from this one here, that is strain T, then from this portion here, that is strain Y. So therefore this is strain T minus strain Y. Okay, that is for the small triangle. Then how about for the big triangle? Okay, so for the big triangle, so this side here, okay, so you will be using this portion here, so this one, so this is 0.25. okay, so the 0.25 coming from 0.9 minus 0.65. then this distance here, okay, this distance, that is 0.005 minus strain Y. Okay, so let me write it here. This is 0.25, then this is 0.005 minus strain Y. Okay, so using similar triangles, so we have phi minus 0.65 over strain T minus strain Y, which is equal to 0.25 then over 0.005 then minus strain Y. So cross multiply, phi minus 0.65 is equal to 0.25 times strain T minus strain Y then over 0.005 then minus strain Y, then transpose negative 0.65. Therefore we have phi, which is equal to 0.65 plus 0.25 then times strain T minus strain Y then over 0.005 minus strain Y. Okay, so this is now the formula. Okay, the formula for phi at transition region when Fy is not equal to grade 60. Okay, or your steel is a non pre-stressing steel. Okay, so be careful on the formulas that you will be utilizing because there are conditions there. Okay, so that one, so this one here, okay, this formula mentioned here, okay, so this formula mentioned here is intended only for steel with grade 60 and for pre-stressing steel. Okay, so that is for the transition region. So again, we don't have any problem with tension control because that would be automatically equal to 0.9, and for compression control that would be automatically equal to 0.65. We'll try to solve some of problems for this one. Okay, so let me just continue the discussion. So again, so that is for P, then compression control. So just always make sure that you need to solve strain Y as well, not to make sure that it is transition controlled or tension control or compression control. Okay, so that is for all for the concepts for the analysis, concepts and procedures for the analysis of singly reinforced beam. So stay tuned guys for our examples.